The goal of this video is to learn how to determine the sample size you need when trying to estimate a proportion. If you've ever paid really close attention to polls, you may have noticed that very often they survey just over 1,000 people. So where did this 1,000 come from? That's what we're going to learn. When planning any study, determining the number of observational or experimental units that are needed is an extremely important consideration. This is our sample size. If the sample size is too large, we're unnecessarily wasting time and resources and unnecessarily exposing our observational or experimental units to any risks or inconveniences that might be associated with being studied. On the other hand, if our sample size is too small, we won't be able to investigate what we want to investigate, and we won't have precise enough estimates in order to be able to make meaningful conclusions. The topic of this video in particular is determining the sample size when our goal is to estimate a population proportion, and we do so with sample data collected from a simple random sample from the population. Here's an example of a typical poll published on the Toronto Star newspaper's website in 2011. Rob Ford became Mayor of Toronto on December 1, 2010. He was elected on a platform that he called Respect for Taxpayers. This included the elimination of any spending in the city budget that he felt was unnecessary. Of course, the reality of implementing budget cuts is always difficult and controversial, and, as the headline suggests, the people of Toronto's support for the cost-cutting dropped as they saw programs important to them being eliminated. I've extracted a few excerpts from the article so that we can talk about the numbers. In particular, 1,046 people were surveyed. Of these, 42% said that they approved of the job Ford was doing during the budget-cutting process. And the margin of error of this estimate is plus or minus 3%, 19 times out of 20. 19 times out of 20 is 95%. Using the methodology used for this poll, and assuming, rightly or wrongly, that the only error is due to the variability in the sampling distribution, a 95% confidence interval for the proportion of adults in the entire city of Toronto who supported Rob Ford is our estimate, 42%, plus or minus our margin of error, 3%, for a 95% confidence interval from 39 to 45%. Let's step back now to the planning stages of the poll. In polling, a 3% margin of error for a proportion has become a standard value, accepted in most circumstances, resulting in a confidence interval with a range of 6%. We saw in the last video that a margin of error for a proportion is a value from a normal distribution or a quantile, z alpha over 2, times the square root of p times 1 minus p divided by n. Suppose we know that we want our margin of error to be 3% for a 95% confidence interval, and we want to see how many people we need to poll. Since we want a 95% confidence interval, as we saw in the previous video, our normal quantile is 1.96. So we let the margin of error be 0.03 and take our formula and solve for n. There is, of course, a complication here. We haven't collected any data yet, so we don't know what p is or we don't have an estimate for it. The typical course of action is to take the worst-case scenario. Since we don't know what p is, we'll plug in the value that would result in the largest margin of error. Then if our estimate of p is something else, we'd end up with a smaller margin of error, which is better than getting a larger one than what we planned for. Our margin of error includes the expression p times 1 minus p. Here's a plot of that for p ranging from its possible values 0 to 1. We can see it's a quadratic function that has a maximum value which occurs when p is equal to 1/2. So that's the value of p that maximizes our margin of error. Plugging in p equals 1/2, solving for n, gives 1,067 as the necessary sample size. Any pools you've seen that have a sample size a little bit bigger than 1,000 have used a calculation like this. What if we wanted a smaller margin of error, say 1% or 0.01? Solving the equation, again using p equals 1/2, the worst case scenario for the margin of error, gives 9,604 for our required sample size, which is 9 times the 1,067 that we saw for a margin of error of 3%. So to cut the margin of error to 1/3 of its previous value, we need to increase the sample size 9-fold. Similarly, if we wanted to halve the margin of error, we need 2 squared or 4 times the sample size. So lowering the margin of error is expensive in that it requires a much larger sample size. How would the required sample size change if we wanted a 99% confidence interval instead of a 95% confidence interval? Your intuition might tell you that we need a larger sample size to have more confidence. And indeed, this is correct. Let's stick with our margin of error of 3% or 0.03, and for our normal quantile z alpha over 2, we'll use 2.576, which is the value that we require for our 99% confidence interval. This gives a sample size of approximately 1,843. So we need about 800 more people than we needed for the 95% confidence interval. If instead we wanted 90% confidence, you could probably guess that we'd need fewer people, and indeed in that case we'd only need 752. Here's another City of Toronto poll from the Toronto Star. As the headline says, this one was massive. They surveyed 12,848 people. Why did they include so many people in their sample? The City of Toronto is broken down into 44 wards, and the researchers wanted to be able to estimate the proportion of Ford supporters on a ward-by-ward basis. The article claims that the margin of error of this poll, with 95% confidence, is 0.9%. While that may be true for a proportion calculated using data from all 12,848 respondents, it's not true for any estimates on a ward-by-ward basis. If we assume that there are equal numbers of respondents in each ward, which probably wasn't the case, but let's use that as an approximation, then dividing up the 12,848 respondents among the 44 wards gives about 292 respondents per ward. The resulting margin of error, 5.7%. This situation also illustrates something we must always keep in mind with confidence intervals. If we have a 95% confidence interval, we expect it to cover the population proportion 95% of the time. In other words, 95% of such intervals include the population value that we want. The flip side of that is that it misses 5% of the time. Unfortunately, we never know whether we're in the 95% or in the 5%. However, with 44 confidence intervals, one for each ward, we have a pretty good chance that we've missed the true P in at least one of those confidence intervals. Since we expect to miss about 5% of the time, in 44 confidence intervals, we'd expect to miss the true proportion about twice. But we don't know in which of those wards we missed it. This situation with confidence intervals for each of the 44 wards in Toronto illustrates a situation where we need to be cautious in interpreting polls. In any situation where we have multiple polls, a common example is the daily tracking of public opinion on a matter, and we have a 95% confidence interval for each poll, we expect then that 5% of the confidence intervals will miss what we're trying to estimate. That's not a problem. It's exactly what we expect from the randomness in the sampling process. We just have to be careful not to interpret the results as if the results of all of the polls together will all cover all of the population parameters 95% of the time. And no matter how large our sample size for a poll is, the resulting confidence interval likely won't capture the population proportion If the procedure suffers from non-response bias, in which part of the population is missed in the polling process, maybe some people don't want to participate, or it suffers from improperly worded questions that lead to response bias. The procedure to construct the confidence interval assumes we have a simple random sample, so that every possible sample from the population is equally likely to have been chosen. Polling organizations have complicated methods for dealing with the bias that results from people not responding to their polls. Each organization has their own proprietary method, which is sometimes why you see results from different organizations that don't agree, and why some organizations are sometimes accused of their own biases.